In this lecture, we are going to discuss about isolated essential singularity, removable singularity, and pole. First is isolated essential singularity. Isolated essential singularity. If the principal part in the Lorentz series expansion, expansion of the function fz about the point z equal to z naught contains infinite numbers of terms, then z equal to z naught is said to be isolated essential singularity of fz. Essential singularity of fz of the function fz. If you recall the Lorentz theorem, that is, if fz is analytic in a ring-shaped region, the bounded by two concentric circle C1 and C2 with radii R1 and R2 less than R1, and z is any point in T, then fz can be represented by infinite series of the form n equal to 0 to infinity a n z minus z naught to the power n summation n ranges from 1 to infinity b n z minus z naught to the power minus n, where a n is my 1 by 2 pi I integral over C1 f of w dw w minus z naught to the power n plus 1 bn is equal to 1 by 2 pi I integral over C2 then w minus z naught to the power n minus 1 f of w dw, where n ranges from 1 to 3 dot dot dot. Here this part is known as principal part, and this part is known as analytic part. If the principal part contain infinite number of terms, then z equal to z naught is called isolated essential singularity of the function fz. For example, consider the function fz equal to sine 1 by z. Here z equal to 0. Here z equal to 0 is a singular point of this function fz. If I put z equal to 0, this function will be undefined. Here z equal to 0 is isolated essential singularity essential essential singularity of fz, or singular point of fz, singularity of fz, because because fz equal to sine 1 by z. We know the sine series is 1 by z minus 1 by 3 factorial z cube plus 1 by 5 factorial z to the power 5 goes on. Since these are in negative powers of z, so the principal part in the Lorentz series expansion of fz about the point z equal to 0 on an infinite number of terms, hence z equal to 0 is isolated singularity of the function fz. Next is removable singularity. Removable singularity. Removable singularity. If the principal part, if the principal part, if the principal part in the Lorentz series expansion, in the Lorentz series expansion, expansion of the function fz about the point, about the point z equal to z naught contains no points, no term, then z equal to a, z equal to this point, z equal to z naught, z equal to z naught is said to be removable singularity of fz. Removable singularity of fz. Singularity of fz. That is, this singularity can be removed by appropriate choice of this point z naught. Okay. If the principal part in the Lorentz series expansion of fz about the point z equal to z naught contains no term, then the singularity is called removable singularity, and this kind of singularity can be removed by suitable choice of the point z naught. For example, for example, fz equal to sine z minus 1 by z minus 1. Here, denominator, when denominator is 0, that is z equal to 1, is the singular point of this function fz. But if we expand fz, we can see that this will be z minus 1. This will be, you use the formula for expansion of sine x, that is z minus 1 minus z minus 1 by 3 factorial plus, this is cube, z minus 1 to the power 5 by 5 factorial dot 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 bracket close. If I expand this, this is 1, this is z minus 1 square by 2 factorial, this is plus z minus 1 to the power 5 by 5 factorial dot dot dot. Here we have seen that there is no negative powers of z minus 1. That means z equal to 1. Therefore, z equal to 1. Therefore, z equal to 1 is removable singularity. Removable singularity of the function fz. Okay, removable singularity of fz. Okay, next is pole. If the Lorentz series expansion of the function fz about the point z equal to z naught contain finite number of terms, then it is said to be, then the singularity is said to be pole. So right, if the principal part, if the principal part principal part in the Lorentz series expansion. In the Lorentz series expansion, Lorentz series expansion of the function fz about the point z equal to z naught contains finite number of terms, finite numbers of terms, say finite number of terms, say then z equal to z naught is called poles of order m. That is if m is 1, then z equal to z naught is said to be simple pole of fz. Okay, if you recall the Lorentz series expansion of the function about the point z naught, that is this n ranges from 0 to infinity a n z minus z naught to the power n. Here it is b1 by z minus z naught plus b2 by z minus z naught. If it is a pole of order m, then here in the principal part there will be m terms. Okay, that means in this case z equal to z naught, in this case z naught is pole of order m, pole of order For example, consider the function. For example, consider the function fz equal to 1 by z minus 1 square. Here z equal to 1 is the singular point of fz, and it is here z equal to 1 is pole of fz, or pole of order 2. Here z equal to 1 is a singular point of fz, and it is a pole of order 2. With that, I would like to conclude. Remaining will be in the next lecture. Thank you.